Have you ever looked up at the night sky and wondered about the biggest things in the universe? We think about vast galaxies and the endless expanse of space. It fills us with a sense of awe. But what if the greatest mysteries are not in the vastness above, but in the tiniest spaces imaginable? What if we could zoom in, far beyond what any microscope can see? What happens when we reach the very fabric of reality itself? Is there a point where space and time simply stop? Or does a new, stranger universe begin? This is one of the most profound questions in all of science. The first ingredient is the speed of light, known as CE. It is the ultimate speed limit in the universe. The second ingredient is the gravitational constant, G. This number determines the strength of gravity. The third and final ingredient is the Planck constant, h bar. This is the fundamental constant of quantum mechanics. In the year 1900, the German physicist Max Planck had a brilliant insight. He realized that you could take these three fundamental constants and combine them in a unique way. The Planck length is incredibly small, around 10 to the minus 35 meters. To put that into perspective, imagine a single grain of sand. Now, imagine scaling that grain of sand up to the size of the entire known universe. To truly grasp the significance of the Planck scale, we must embrace the Heisenberg uncertainty principle. The more accurately you know where a particle is, the less accurately you can know where it is going. To see something as small as the Planck length, you would need to concentrate an enormous amount of energy into a very tiny space. The very act of trying to observe something at the Planck length would create a microscopic black hole that swallows your experiment. String theory suggests that if you could zoom in on any fundamental particle, you would discover it is actually a tiny, vibrating, one-dimensional loop of energy. In this view, the universe is a grand cosmic symphony, and the laws of physics are the rules of harmony. Loop quantum gravity takes a completely different approach, suggesting space is a network woven from quantum threads or loops. From a distance, it looks smooth, but up close you see it's woven from a network of one-dimensional threads. The holographic principle suggests that all the information needed to describe a volume of space can be encoded on a two-dimensional surface that surrounds it. Perhaps our three-dimensional existence might be a holographic projection of information stored on a distant surface. Imagine we had a magical probe that could shrink down past the Planck length into the realm beneath reality. What would we find there? Would the laws of physics that have served us so well simply switch off? As we cross the Planck threshold, this smooth stage could shatter. Perhaps the dimensions we know are not fundamental at all. The universe might not have 3 dimensions or 10, it might have a fractional number of dimensions. A compelling answer from the frontiers of physics is information. The most fundamental level of reality might be made of tiny bits of information. The universe is not a great machine, it is a great computation. Below the Planck scale, the neat, orderly procession of cause and effect might break down into chaos. Events might exist as a network of relationships, where some events are linked but not necessarily ordered. Below the Planck scale, we might come face to face with a unified superforce in its pure form, but we might also find completely new and alien interactions that only operate at these incredible energy scales. In the sub-Planckian realm, matter might be a form of pure energy or pure information, existing in a state we have no language to describe. This pre-matter might be the common ancestor of all the particles we see today. We have journeyed to the very edge of reality, to a scale so small that it challenges our ability to think. This is the Planck scale. It's a frontier defined not by a lack of technology, but by the fundamental laws of nature themselves. We are living through a period of immense scientific revolution, similar to the time when Newton was formulating gravity or Einstein was developing relativity. Finding this theory, often called a theory of everything, is the holy grail of modern physics. The questions we are asking are the same questions that humans have asked for millennia, looking up at the stars in wonder. This exploration belongs to all of us. It's a testament to our relentless desire to push beyond the known. So the next time you look up at the night sky, remember that a mystery just as vast lies in the opposite direction, in the impossibly small spaces that form the very foundation of everything you see, and wonder.